Okay, let's see yet another example. Given the following language description, W in again 0, 1 star, such that we want a number of zeros in W to be equal to the number of ones in W. What could be an example string that belongs to the language? For instance, if I take W to be equal to 0, 1, 1, and then 1, 0, 1, 0, 0. In this string, I have in total 4 zeros against 4 ones. So number of zeros is equal to number of ones. Thus, this string belongs to the language. Remember that previously we had designed a PDA for the language that consisted of n zeros followed by n ones. Okay? For such a language, it was easy to come up with a PDA that recognizes it, because what we were simply doing in terms of the informal idea, we were storing the zeros that we see in the first half of the string and making a non-deterministic guess at each time that we have reached the middle, and after that point we were basically comparing the number of symbols that we have stored in the first half, whether they are the same as the number of ones that we see in the input string. Okay, so the idea for such a language was kind of simple. However, with this language, we don't have a specific order determined for the symbols 0 or the symbols 1. They can be in any order as long as their number, their count overall is the same. So how can we solve this? How can we design a PDA that will recognize all such strings? Again, let's first try to describe the informal idea to design such a PDA. What we will try to do is the following. Again, obviously we should make use of the stack that is available to us to do any type of indefinite counting. Okay. Well, for this language, how we will use the stack is the following. In the stack, at any point during the processing of the input string, so if we have processed the input string up to this point, in the stack we will keep however many extra symbols there are when compared against each other. So if this is the part of the string that we have processed so far, number of zeros we have seen is 1 more than the number of ones. So in this case, we want to store a single 1 in our stack, indicating that in the part of the string we have seen so far, there is 1 more 0 than the number of ones. After processing the next symbol, now in here we have their number is equal, so we want the stack to be empty. In here we want the stack to contain a single 1 corresponding to the extra 1 that we have against the zeros. At this point we want the stack to contain 2 ones, because number of ones is 2 more than the number of zeros. At this point we want the stack to contain a single 1. At this point we want the stack in this point it was 2 ones, yes. At this point we want the stack to contain a single 1. At this point we want the stack to contain yet again 2 ones and a single 1 and nothing in the stack. So if we can somehow in the stack store the number of extra zeros or extra ones, whichever one is extra, if we can store that count, it seems that we have a good idea to recognize such strings. So that will be the main idea. Each time on the stack, make sure that you have as many symbols as the extra symbol. Okay. At any point during the computation, store as many extra symbols, let's say extra symbols x as the difference of let's say number of x's that we have seen so far. Let's denote it with nx, and let's say the number of the other type of symbol y with ny. With the we want to keep this many symbols x on our stack, on the stack, if obviously nx is greater than ny. So let's say at some point, if we have seen nx many symbols zeros in the input string and ny many symbols 1 in the string, then we want to keep as many symbols 0 in the stack as the difference. Okay, because this way we will be able to, if the next symbol is simply a 1, we will be able to remove a symbol 0 from the stack to decrease that difference. Or if we see yet another symbol 0, then we will be able to introduce yet another 0 in the stack to increase this difference. And also we will be able to check whether this difference is 0 or not, meaning that the number of zeros or ones that we have seen so far is equal, by simply checking whether the stack is empty or not. So we will do this if nx is greater than ny and otherwise, and vice versa, meaning that if we have extra y's, extra symbols y as compared to the symbols x, then we will keep ny minus nx many symbols y on the stack, where x and y basically stands for the symbols that we have in our alphabet, zeros and ones. Okay. Now the important thing will be how to implement this main idea. Okay. So to implement this, or in terms of making the representation of our state transition diagram simpler, we will introduce a more generalized transition. So basically we will allow our transitions to be able to push more than a single symbol at a time. Normally our transitions, our traditional transitions in our state transition diagram, are doing a single push action. So each transition is of the following form: read a symbol from the inputs, pop some symbol from the stack, and push a single symbol into the stack. We will try to generalize this transition so that we can push multiple symbols with the same transition. So basically, for ease of diagram depiction, consider that we introduce the following types of transitions. If we have Qi, we will allow transitions of the following form. Just some generic transition A, B, C, D. So basically this part is the same: read the symbol A from the input alphabet, pop symbol B from the stack, push now two symbols, first D and then C. Note that this is actually equivalent to, in terms of our traditional transitions, this is equivalent to having two transitions. So Qi, basically in the first transition A, B, and first push D. So read input symbol A, pop B from the stack, and push D first on the stack, go to an artificial state QA, and then without doing anything on the input and popping anything from the stack, simply push the second symbol that we want to push, C, on the stack. And this is QJ, the same destination state that we want to go to. So note that this generalization doesn't is legal because we have shown that it can be done with two of the traditional transitions. Okay, so for this example PDA state transition diagram, we will allow such transitions, which just not for the sake of not making the state transition diagram too complicated, but you should be able to notice that the same thing can be done using the traditional transitions as well. Okay, let's get back to seeing how we can design our PDA using this main idea. The main idea, remember, was to keep on the stack as many extra symbols as the extra one, and if we can keep the stack to store that many symbols at any time, then upon processing a new symbol from the input tape X, let's say if we see a new symbol 0 on the stack on the input tape, and if we have 4 zeros in our stack, this means that so far the number of zeros is 4 more than the number of ones. And if we see a new 0 in the input tape, we can easily increase the difference to 5 by simply pushing a 0 on the stack. On the other hand, again the same scenario, if we have currently 4 zeros in our stack, meaning that the number of zeros in the input part that we have seen so far is 4 more than the number of ones, and if we see a symbol 1 in our input tape, this means now we will have 3 extra zeros. In order to implement this, we will simply pop a 0 from the stack. Okay, so to implement this with a PDA, we have the following. So this is our, again, initial starting state Q0. Again, our normal transition, the first initial transition, to check to push the delimiter dollar so that we can check empty stack condition. At state Q1, we will repeat doing the following. Okay, if we encounter a 0 from the input tape, and on top of the stack, from the top of the stack, we have popped a 1. Note that what is the meaning of popping a 1 from the stack? It means that if we are carefully applying this idea correctly so far, it means that the number of ones on the stack, the number of ones in the inputs were more than the number of zeros, and the stack contains exactly that difference, many ones in the stack. Okay, but now we have seen a 0, so which means that that difference is decreased by 1. We need to remove one symbol 1 from the stack, but for this we don't need to do anything, because note that this transition corresponds actually to popping a symbol 1 already. So this means that we don't push any symbol into the stack. Again, let's repeat. If at some point we had, let's say we are up to now, we have processed the input string up to this point. Okay, let's count the numbers. We have 3 ones and 1 0. We have more ones than zeros, and the difference is 2. If we have done everything, if our machine has done everything correctly, it should normally have the difference many ones on the stack, so it should normally have 2 ones on the stack. So dollar and 1 if everything is done correctly by the machine so far. Upon encountering a symbol 0, at this point now the difference has decreased to 1. So the difference between the number of zeros and the number of ones is simply 1, which means that after processing the symbol 0, we should be removing a single 1 from our stack. And this is exactly what is done with this transition, because this transition says if you see a 0 from the input string and if there is a 1 on top of the stack, remove that 1 from the stack, because this already corresponds to popping or removing an item from the stack. The same will be true for if we read a symbol 1 from the input, and if on top of the stack we have a 0, don't push anything into the stack, because number of zeros were extra compared to the number of ones, and that extra amount is already stored in the stack. But I have seen a single 1 and I have now removed a corresponding 0 from the stack. I have removed an extra 0 from the stack. Now, how about for the rest of the possible scenarios? If the input is a 0 and on top of the stack we also have a 0, what should we do in this case? Note that in such a case, the number of, if we have popped a 0 from the stack, this means that the number of zeros we have seen so far in the input is more than the number of ones. And yet we have seen another extra 0, which means that we have to increment the difference which is stored in the stack by 1. To do this, we need to push 2 zeros on the stack, because 1 push corresponds to popping the symbol 0 from the stack, because this is naturally a pop, and the second 0 corresponds to the extra 0 that we have seen in the input. We need to do the same thing if we see a 1 and the top of the stack is a 1 as well. Note that, for instance, this case will happen. Let's consider the following scenario. We have so far read 3 symbols of this string. So far we have read this part of the string. If everything is done correctly, on our stack we should normally have dollar and a single 1, because the difference between the number of ones and zeros is 1. So we have a single 1 on our stack. If we read the next symbol from the input, which is a 1, so we read a 1 from the input, and we pop the symbol from the stack and see that it is a 1, note that I say pop, which means we are actually removing this 1. And after reading this 1, we need to now have 2 more extra 1s in the stack. Because this is already removed, then we need to push 2 1s into the stack, so that now we have dollar, 1 and 1 upon finishing the processing of the first 4 symbols of the string. Other cases may arise as well. It could be the case that we read a 0 from the stack and we have a dollar. What is the meaning of this configuration? It means that up until now, upon processing the part of the string up to this point, the number of zeros and the number of ones is equal, and yet we see another 0. After processing this symbol 0, now we know that number of zeros is 1 more, so in the stack we should keep 1 extra 0. To do this, we push 0 and dollar. Why do we push the dollar? Because with this transition, this operation already pops and removes the dollar. This means that we should first push that popped delimiter dollar and then push our extra 0 on the stack. The same goes for if we see a 1 in the input and the popped symbol from the stack is a dollar, we push 1 and dollar. These are all the possibilities. So we keep on repeating consuming symbols from the input and popping symbols from the stack. And when is it that we should go to an accepting state? So we would go to an accepting state Q2 if at the end, upon finishing the whole string, if our stack is empty, which means that the difference between the number of zeros and the number of ones that have been processed so far is simply 0, which implies that their counts is equal, then we will go to the accepting state. So if the input string processing is finished, we read epsilon from the input, and the stack is empty, which can be checked by reading dollar from the stack, and we simply push an epsilon and go to the accepting state Q2.